We're going to continue in this lecture with series. So last time we sort of discussed the first few topics and we introduced two new ideas. Now, the simple one is the nth term test, and then the slightly more involved one, which just involves integration, was the integral test. Both rely on certain conditions, and at least the integral test is quite powerful. Today we're going to look at a couple more ideas that you can use on various series. Now remember, the motivation for studying series is, all right, a couple of lectures ago we talked about Taylor polynomials, and the idea was, all right, if I keep adding bits to my Taylor polynomial, will I actually get a function like, I don't know, cosine x or sine x? The answer is yes, in certain cases. So what we're doing with all this series stuff is just laying the foundations to come back to all that stuff, because it's quite interesting. All right, the comparison test. Now, the comparison test, like the name suggests, just involves you comparing a given series with another series that you construct. Okay? Think back to the squeeze or the pinching theorem from limits. So it's up to you to construct a suitable function. This kind of idea is very similar. Now we're working with series with no negative terms. One of the reasons for that is because when you deal with adding positive or non-negative things together, the sequence of partial sums is an increasing or non-decreasing sequence. That's important for the kind of arguments we're going to use. So what does the comparison test say? Well, there's two parts to it. Suppose sigma an is some given series. Now, if you can construct a new series, sigma cn, where an is less than or equal to cn for each n. How you doing? You missed all the action, man. There was like 2 proposals. I'm not kidding. Did you know about this? Oh, it was. Oh, yeah, I was sure it'll be on YouTube. Oh, by the way, can I just have a show of hands? Who's actually had a look at any of the UNSW math YouTube videos? Anyone? All right. I've got some interesting news. YouTube just made me a partner, so yeah, I'm pretty happy about that. They say, well, we had a look at your site. You'd be an excellent partner in education. So yeah, I'm pretty happy about that anyway. Thank you. Anyway, back to the comparison test. Otherwise, I'll be editing this for hours. If you have this relationship and the bigger series converges, then the smaller original series has got to converge. So it's a bit like the pinching theorem or the squeeze theorem with limits. Although you don't actually calculate what this series is. Okay, so just the way I remember this is if you have this kind of relationship and the bigger series converges, the smaller series has also got to converge. That's all it is. Okay, and sort of on the other hand, if you have this kind of relationship, so sigma an still your original series, and you've got some construction d sub n where the smaller series diverges off to infinity, it's got to push the original series off to infinity. So the original series has got to diverge in that respect. Now the proof just uses the corollary at the start of the previous section. In other words, a series of non-negative or positive terms converges if and only if its partial sums are bounded above. Okay, it's like the monotone convergence theorem that was at the end of sequences. Anyway, that's not examinable, so don't worry too much about that. The big question here, from a practical point of view, is, well, how do I choose the Cn or the Dn? That's the real important thing, because that's what you're going to be doing in, when you're solving these kind of problems. Well, in general, we make a comparison with some sort of p-series. So, I don't know, 1 on n squared, sigma 1 on n squared, or sigma 1 on n, or sigma 1 on n cubed, something like that. So let me show you how this works, and let's do some examples. Okay. Discuss the convergence, divergence of this. Here I've got k's. It doesn't really matter. It's just a dummy variable. So I'm just going to, oops, here, a sub n is this. Now, what rules do we know about series? Let's take the limit as n goes to infinity of a sub n. What do we get? We get 0. So the nth term test tells us nothing about this. It could converge, it could diverge, we don't know. We could use the integral test perhaps on this, but you'd have to integrate this and see what happens. So what we're going to do is use this new comparison test. So what I have to do is compare this with some sort of C sub n or D sub n. So what I propose is, okay, you can see that this is all, if I take away that plus 3, it's almost like a p-series. Right? So what I'm going to do is actually compare that with 1 on n to the 4th, just 1 on n to the 4th, right? So here's my p-series, sigma 1 on n to the 4th, and we know that the series associated with this converges. So we're going to construct C sub n to be 1 on n to the power 4. Now, you might be thinking, well, why didn't you let that be dn or something? Well, I know that this converges. So is a p-series with p equal 4. Now, remember the power p is important. Here the power is 4 and it's strictly greater than 1. That means the series has got to converge, this new series. So, what do we have here? I'll just put this over for a second. It's the first situation. We've got this kind of relationship with C sub n equals 1 on n to the 4th. And we know that this converges. So it's got to force the original series to also converge. That's it. So I've pretty much mentioned everything I need to mention there. I've justified my conclusion by mentioning the test that I'm using, the comparison test. So you can see, at least in this example, how p-series are really useful. Really, really useful. Now, yes?
So what you're saying here is you says that since n to the power 4 plus, we don't know if it's diverges, we use 1 on n to the power 4 as a convergence, right?
Correct. There's like a comparison series. Yeah. So what you do is, if you've got a complicated series, compare it with a simple series that you know converges, or that you know diverges. Depending on the inequalities, you can hopefully get what you want. Any other questions for that one? Now, you don't have to, of course, make this choice. You could make this choice, you know, in another way. It could be something like 1 on, you know, what have we got? 1 on n cubed. Okay, it could be 1 on n cubed. That would be fine. So the choices here are not unique, not necessarily unique. But when you see a plus down there, it's a dead giveaway, you know. Any other questions for that one? Yes.
If we choose one that's bigger than the original one.
Sorry, say.
So if we choose one that's bigger than
Yep.
the one we have, what
Yep.
happens then?
Oh, it's a good question. So if you had sort of this, if you made a choice where you had the other inequality, right, round the other way.
Do we have an inequality for the region?
Sorry?
Do we have an inequality?
No, you don't. No, that's all you have. So you've got to construct that somehow. Okay? Now, if you chose a series, say your C sub n was smaller than your A sub n here, and the C sub n converged, well, it tells you nothing. Nothing. So you need to make a smart choice. You need to make a smart choice for this guy here. Okay? Now, that'll come with a little bit of experience, but I can help you a little bit. Let's look at another example. Here we don't have a plus down the bottom. We've got a minus. So how does that affect the problem? So what we've got to do is compare this with something that we can use, generally a p-series. What I'm going to do with this one, can anyone suggest something? What might we compare A sub n with? Yeah, 1 over n, right? Is that what you were going to say? Yeah, cool. If you just look at the n cubed minus 1, that's less than or equal to n cubed. So when you divide, switch them up, the inequality sign, and then we can simplify n squared on n cubed. Now, in this case, I'm going to choose d sub n to be 1 on n, because actually, it's going to be part 2 of the comparison test that we're going to apply here. So sigma 1 on n, does that converge or diverge? It diverges, right? It's a p-series with p equal to 1. You know, the intuition here is that, oh, sigma 1 on n must converge. No, it's not true. It diverges. So let me just go back to the comparison test. I'll put the other one back up in a minute. So what we've done, we've actually got this inequality. D sub n is our 1 on n, and we know that this guy diverges. So the original series must also diverge. Now, One thing that's really hard to convey here is how to make the original choice, the original construction for your C sub n or your D sub n. It's something that I guess will come with a little bit of time here. But for these examples, when you've got something like a, here you've got a -1 down here, and you had a +1 in the example before, you can just use simple inequalities on that. Okay? Any questions for that one? Notice again, I've used the conclusion where I've mentioned the test. Yes.
Generally, why would you say that if P is less than or equal to 1?
Yep.
Less than or equal to 1. Why would you say it diverges? Whereas if P is greater than 1, why
Yep.
would you say it converges?
Good question. The question is, I've forgotten the P series test. What's to do with that? Why does sigma 1 on n diverge? Well, the integral test. The integral test. If you integrate 1 on x from, say, 1 to infinity, it diverges. So the integral test says the series has also got to diverge. Right. But you don't have to do that. You don't have to integrate this 1 on x or 1 on n or whatever. Just say it's a P series. It'll save you like 3 lines. Any other questions? Yes.
Classify it as an application of the pitching theorem?
No, strictly no. But I like to think of it as the same, because with the pinching theorem, you actually get the limit. You know what I mean? Whereas here, you don't. So the proof for the main result, it relies on increasing bounded sequences of partial sums, okay, that are positive. That's why we have positive terms. It's a good question. Any other questions? See you later. You did well. Off to the honeymoon. All right. Now, this is coming back to, I think, what you were getting at before this next example. This is a good example of what not to do. Okay? At university, anyone taking physics here? Okay. I remember having a look at, I think Joe Wolf. Joe Wolf's such a good teacher. He had some course pack for physics, and when you open it up, the first page just says how to fail this course. Okay? Do this, don't do that, do this, do this. I don't know if it's still around, but it was really good because at least, we tell you what to do a lot of the time, but it's also, I feel, important to tell you what not to do. So this is an example of what not to do, right? Here, imagine this is your original series, and you've got to find out whether it converges or diverges, just like you would in the final exam. Now you have, the idea here is to set up inequalities. So, but you've got to set them up in a smart way. By log here, I mean natural logarithm, by the way. So I'm just going to write ln here. Now, there's a relationship between log n and n. So, I don't know, n greater than or equal to 2, that's good enough for our purposes. And so if I square these, I'll get log n squared is less than or equal to n squared. Oops. Right. Now what I can do is rearrange that and compare my two, my a sub n and whatever's in here. So let me show you how I do that. Okay, so we're feeling good. We've got some sort of inequality, which is like a, this is going to be some sort of P series when you sum it all up. But what's the problem? Can anyone see what the problem is there? It looks pretty. Anyone? Right, can you say again? Right. If you may be looking at this and going, oh great, this is simple. I know this the series associated with this converges, but the inequalities go in the wrong way. So what you've got at the moment is you're saying that the smaller series converges. And the original series is what you want to determine, whether it converges or diverges. It tells you nothing because you're saying you've got two series, the smaller one converges. It tells you nothing about the bigger one. Okay? Nothing. Nothing. So be careful with your but our inequalities they're the wrong way around. So we cannot apply the comparison test. It's impossible. So what I'm trying to show you with this example, apart from what not to do, is the limits of the test. Like you can't just use one test for every series. When you reach this kind of dead end, go back and think of another test. Can anyone see how we might actually work out whether that series converges or diverges up top? Yep. Yeah, the integral test, right? Very good. The integral test. So in this case, we can apply the integral test. Now I'm not going to do that because we did it last week, but have a go. The series converges. Okay, so when you integrate, when you look at the integral associated with this from say, I don't know, 2 to infinity, it'll converge. The integral test says that the series also converges. So that's one of the limitations of the comparison test. Now, a lot of students, they get really fed up with the inequalities in these tests because, you know, a lot of people think inequalities are quite dry. There's a better way of doing many of these problems. And it doesn't involve inequalities. Okay? It involves an idea called the limit comparison test, where you compare, well, I guess you just calculate the limit of a ratio. So let me show you what that's about. So I'll leave this as an independent learning exercise. Now, a lot of students prefer this test. They're not necessarily interchangeable, but the good thing is that you don't have to muck around with inequalities. So what does this limit form of the comparison test say? Well, suppose you've got series with positive terms. Then there's, I guess, three situations. If the limit of this ratio is some positive number, then the two series have the same characteristics. They either both converge or they both diverge. In part 2, if the limit of the ratio is 0 and sigma bn converges, then sigma an converges. And if the limit of the ratio is positive infinity and sigma bn diverges, then sigma an also diverges. again, it comes down to using these tests in practice. It comes down to making a wise choice for either A sub n or B sub n, depending on I guess, what you want to show. So let me give you an example. We'll come back to this in a second. Let me give you an example of how this works. Now, with these two tests, you cannot get away from the need to construct some sort of complementary or comparative series. Discuss the convergence, divergence of this one. Well, firstly, let's just do a simple test on it. What does the nth term test tell us about this series? The series? Does it tell us anything? I'll tell you what, we'll get back to that. But a very good test before you do anything else is just look at the nth term test. If the limit's not 0, you can say, bang, the series diverges. That's it. A very, very good test. But let's actually have a look at this in terms of the limit comparison test. Now, I'm going to choose B sub n to be 1 on n. Now, the big question is, well, where did that come from? Where did you pull that? For me, a very good idea is to look at the following. Look at the highest power in the denominator. Okay, you've got a square root and a squared, so the highest power there is essentially 1. Look at the highest power of n in the top. It's 0, right? 1 is just n to the power 0. What you then do is make your choice for B sub n, 1 on n to a power. That's the difference between the biggest power down here and the biggest power up here. So the biggest power down here is 1. The biggest power up here is 0. So it would be 1 on n to the 1 minus 0. Okay? Now that will work almost every time. I'll give you an example where it doesn't work, but look at the difference between the two powers in the bottom and the top of the original series, and then just choose some sort of P series with the difference. Okay, that's information you can use. So let's actually this is a P series with P equals 1. And that is less than or equal to 1. So it must diverge. So let's look at the limit, and you'll see why I've made this choice in a second. I'll put this back up in a sec. We want to calculate the limit of these ratios. Okay? And the way I've chosen this is actually going to simplify things quite nicely. So the limit of A sub n on B sub n. Now, so we're going to be dividing one sort of rational function by another, so I'm just going to multiply by the reciprocal. So what we're going to do is look at this limit. Now, just sort of intuitively, the dominating power down the bottom here is n, because you've got a square root and a square. The dominating power up here is also an n. So you would kind of think that the limit of that ratio is going to, or that product, I guess, is going to be something like 1. So what I'm going to do, I'm actually just going to divide top and bottom by n, and then just push that n inside the square root sign down the bottom. So let me show you. So divide the top by n, divide the bottom by n, and then put it turn it into an n squared because you put it inside the square root sign. Okay, so I've been a little bit tricky there. Bless you. All right, so the limit here, you probably wouldn't muck around with all of this in the exam. The limit here is clearly going to be 1. That's going to go to 0. So we've calculated our limit of our ratio. It's a positive number. That means it's situation 1 on our comparison test. So let me show you what I mean there. All right, the limit of this ratio is a positive number. Then we can conclude, if that's true, which it is here, then either both series converge or both series diverge. We've already worked out that this series diverges. So it means the original series has got to also diverge. Okay, LFCT, limit form of the comparison test. Limit form of the comparison test. Now, of course, when you're doing this in an exam or elsewhere, you want to minimise the effort, right? Can anyone tell me why, this is a good question, why we would have expected this to diverge all along? No, someone else. Sorry? Say again? I guess getting back to P-series ideas. What do you notice about, if I cover up this 4, what do I get? I get something like sigma 1 on n. It's a P-series. It's got to diverge, right, with P equals 1. Okay, so don't let that minus 4 fool you. The ideas can actually be traced back to, in this case, a simple P-series. Or any questions for that? The best advice I can give with these kind of questions is look at the highest power in the denominator, the highest power in the numerator, and then make your choice 1 on n to the difference of the power here minus the power here. That's the best advice I can give. All right, so here's one that isn't so straightforward. Again, by log n, I mean the natural logarithm here. This is hard. All right, so we're going to let log n over n to the power 3 on 2. That's just going to be my a sub n. Now, what I have to do is somehow construct a b sub n and then look at the limit of the ratio. Now, this is hard. Okay, so let me just show you the choice that I've made and why I've done it. Okay, I'm going to choose b sub n to be 1 on. Again, it's going to be turned into a p-series, but look at the power here. N to the power 5 on 4. Now, the critical thing with this power is the following. The power is strictly greater than 1 and strictly less than 3 on 2. Now that's going to be important That's going to be important. In fact, you can choose any power here that satisfies this sort of inequality, and it'll still work. Okay, now it's not clear why this is necessary, but let me show you. All right, so I'm just going to write out this without the limit at the moment. Now I can get some cancellation there with the powers. And I'm going to end up with something like this, according to my calculations. Now, the big question is, what's the limit? 0. Who said 0? Who said it? Was it you? Someone said 0.
It was me.
Huh?
I can say it was me.
Okay, right, yes. Why do you think it's 0? And how? What does log n on n to the quarter go to 0 as n gets large and positive? Anyone know? Yeah, well, I guess there's a couple of ways of working it out. One sort of formal way would be L'Hopital's rule, but the important thing here is that the limit does go to 0. So what does that mean? Well, let's look back. It's part 2. If the limit of the ratio equals 0 and the chosen series that we've chosen in this case converges, then the original series must also converge. So does the series associated with this converge? Yes, because it's a P series. And the power is greater than 1. And so, by part 2 of the limit form of the comparison test, our original series must also converge. Now, camera. Okay. Now, this is a frustrating question because it's not clear. Well, let me give you an example. What happens if I chose 1 on n there? Okay? The limit wouldn't work out the way you wanted to. So you couldn't apply the limit form of the comparison test there. So the critical thing for this one is that the power of this choice here satisfies this. And actually it's quite common to actually sit down and do some of these problems and make a choice, an initial choice for your B sub n, and then it doesn't help you. Then you've got to go back and make another choice until it gets you what you want. Now with experience you'll be able to do that effectively, hopefully, before the exam. So that's a tough question. It's a tough question. Now the second thing I wanted to talk about is the so-called ratio test, D'Alembert's ratio test. Anyone heard of D'Alembert? It sounds like a nice cheese or something, you know, D'Alembert. D'Alembert's ratio test is quite nice and it's easy to apply. You don't have to choose anything. You just look at a limit of a certain ratio. All right, so what is it? Again, suppose we've got a series with positive terms, and suppose you're looking at the limit of this ratio, and the limit's some value. If this limit is less than the series, D'Alembert's test says the series converges. if the limit is greater than 1, then the series diverges. This is what this test says. And the important thing is, if the limit of the ratio is 1, the test tells us nothing. Absolutely nothing. So if you go and try to apply this and your limit's 1, well, you've got to go back and use another test or use another idea. So I've put a proof in here. I'm not going to go through it, but a good idea from a practical point of view is to think of using D'Alembert's ratio test when series involving factorials or exponentials are involved. So let me show you what I mean. Oh yes, D'Alembert, he got his face on a French stamp. You know you're doing pretty well when that happens. So, yeah. Okay. All right, these are fairly easy to do and an easy test to apply. You just got to watch the algebra. Generally, a lot of things cancel when you're doing the calculations here. So, a sub n plus 1. So replace n with n plus 1 in brackets. Now, a lot of students, I'm not going to put the brackets in there, but a lot of students actually screw up the algebra at this step. So let's look at the following. A sub n plus 1 over a sub n. So we're going to look at the limit of this ratio. So all I've really got to do now is look for some cancellation. So I'm going to expand these powers, I guess. So I can cancel that off. I've still got a 2 to the power n floating around. So can anyone suggest, because we're going to have to take the limit here, can anyone suggest what we might do to take the limit? Because that 2 to the n's in the top and the bottom. Huh? Divide by 2 to the power n, top and bottom. Good idea. Who said that? Someone said it. All right, so let's do that. So now we can take the limit on the and the limit on the bottom. So this is going to go to 0, this is going to go to 0, so I'm going to be left with 2/3. Okay, so what does that mean? Well, let's go back. If the limit's this number here and it's less than 1, the original series converges. Okay, so this is row, as in row, row, row your boat, or row hypnol. So part A of the ratio test tells us that our original series must converge. Now, the nice thing about this test is that there's no inequalities. You don't have to make any choices for comparison series or anything like that. you just look at the ratio and take a limit. Is the limit less than 1 or greater than 1? If the limit equals 1, well, you've got to go back to the drawing board. Any questions? All right, let's have a look at this one. Factorials. Factorials. So here, this is our a sub n. And a sub n plus 1 is this. So let's look at the ratio. The nice thing about factorials is you can cancel them off in many cases. So right, so let's consider the ratio of the following. Again, we can just try to simplify it. So we can break these up, we can break this up, and we'll get the following. Now, breaking this up, just be a little bit careful here. Okay, so it's getting a bit messy, but we're going to cancel off in a minute. All right, so cancel time. Let's oh, okay, I can cancel that one off as well, can't I? So now if you look at this, the dominating term is going to be something like 4. So we're going to have a 4n on top and a n down the bottom. So this is going to go to 4. Now, the limit, this limit here is strictly greater than 1. And so B of the ratio test tells us our series diverges. Okay, now I know I've gone 1 minute over time, I'm sorry about that. Independent learning exercise. What happens if you try to apply the ratio test to this? Well, in that case, the limit of the ratio is 0, so the limit's 1, so it tells you nothing. Another way of doing this, a much faster way, again, don't get tricked into just, oh, here's a problem, here's the technique. You can actually apply the nth term test to that starred series, and it's not 0. So that series got to diverge. You can actually do this problem in one line. All right, guys, I'll see you all tomorrow.